Hello once again, class, and welcome to another mock lecture. We're continuing on with the Math 111Z prereq stuff. I'm calling this one video 3. We're going to cover two topics, but again, they're very closely related. This one's about average rate of change and the difference quotient. Now to set this up, let's think about the line y is equal to mx plus b. M is the slope of the line, right? So when you have something like y is equal to 1/2 x minus 1, 1/2 represents the slope of the line, no matter where you look. You go up 1 over 2, up 1 over 2, up 1 over 2, or you could go backwards, down 1, to the left 2, if you're going to count that way, and you're starting at -1 because that's what the y-intercept is. Or maybe you don't know the equation of the line and you just have 2 points and you want to find the equation of the line. Well, there's a slope formula that we could use to figure this out. It's y2 minus y1 divided by x2 minus x1. And here I'm calling x1, y1 the 2, 0 coordinate and x2, y2 the 6, 2 coordinate. And then I just plug that into the formula and I get 1/2. Right? So that's how the y is equal to 1/2 x minus 1. But what we're going to be talking about today is, can we find the slope of nonlinear functions? So something that looks like this. And the answer is yes, but it's not the same everywhere, right? Unlike a line, nonlinear functions don't have the same slope everywhere. Every single point on the line is going to have a different slope because of the curvature, right, of the graph itself. There does exist slopes at a point. For example, there you could find the slope at C, but that's something that you talk more about in a calculus class. But in this class, we're going to focus on finding an average rate of change over a specific interval. So let's say that I want to find the average rate of change between the 2 points A and B here. What you're doing essentially is you're figuring out, look, I see that the slope kind of starts at negative and then it turns positive, and it's positive for more than half the distance from A to B. So you'll notice that we started in a lower position and ended in a higher position. So you'd imagine that the average slope over this interval would be something that's positive. And as it turns out, all we need to do is actually just find the slope of the line that connects those 2 points. And that actually is the average rate of change, right? The slope of this line is the average slope for this blue part only, right? And that's important to know. It's not the average rate of change for the entire line or the entire graph of f. It's only the average slope for this little kind of valley part, I guess, is what I would describe it as. Or to be more specific, it's the average rate of change on the interval a to b, the closed interval a to b, I should point out. Well, we know how to find the slope of a line. It's y2 minus y1 over x2 minus x1. We just need to know what are its y values, but we can find them because we know the function f. Right? Whatever b gives you when you plug it into f, f of b is going to be y2. Whatever a gives you when you plug it into f, f of a is going to be y1. So we plug all that stuff in and we very quickly find that the average rate of change on the closed interval a to b is f of b minus f of a divided by b minus a, which is just basically this, which is really nice because I always tell students, look, slope is slope. No matter what you're doing, whether you're finding the slope of a line or you're finding the average rate of change for a non-line, really? A nonlinear function, then you're just using y2 minus y1 over x2 minus x1. Except in the context of a nonlinear function, we're calling it f of b instead of y2 and f of a instead of y1. So in practice, this is relatively straightforward. So for example 1, I said find the average rate of g on... You know what that should say, though, is it should say find the average rate of change of g on the closed interval 0 to 3 and also 1 to 6. So we'll do 0 to 3 first. You have to keep in mind that this closed interval 0 to 3, those are x coordinates, right? So this is x1, x2, as it were. I mean, really, for average rate of change, it's a and b, respectively. But you can think about them as x1 and x2. We don't know what the y-coordinates are until we look at the graph itself. Okay, so we notice that at 0, we have the y-coordinate -3, and at 3, we have the y-coordinate 2. So then I'll just do y2 minus y1 over x2 minus x1, which is 2 minus -3, which will actually be an addition, divided by 3, so we get 5/3. Now you might be wondering, well, Mock, can't I just count up and over from point to point to figure out what the average rate of change is? Like go up 5 and over 3? Yeah, you could do that. When you're given a graph like this and you have very clear intersection points, you could totally just count your up and over, your rise over the run, and that is actually the average rate of change. So for 1 and 6, I have different points now because we're looking at the x coordinate 1 to the x coordinate 6, which have different y coordinates, which you'd have to find. They're 1, 1, and 6, 6, though. So if you count up and over, you get 5 over 5. Or if you do y2 minus y1 over x2 minus x1, you also get 5 over 5, which is 1. So the slope of that line is 1, which means the average rate of change of g on this interval is 1, and the average rate of change on this interval is 5/3, which makes sense visually too. The blue line is steeper than the purple one. So one very important thing to keep in mind is that the average rate of change of a function is going to depend on the interval that you choose. I mean, here we got 5/3, here we got 1. So average rate of change will change based on the interval that you pick. But what if you don't have a graph? Right, example 2 says find the average rate of change of q of x is equal to the square root of 2x plus 1 on the closed interval 0 to 4. Well, again, remember, they're both x values. A and b represent x values. Again, we've been kind of thinking about them as x1 and x2, and you can do that. Which means we need to find the corresponding y values. Here we don't have a graph to just look at it and see what it is. We're going to actually have to evaluate q at these specific x values. So we have to plug in 0 and we have to plug in 4 for the function. Plug it into that x there. So if we do that, we get 1 for the corresponding y value for the x value 0, and we get 3 for the corresponding y value for the x value 4. And those are your y1 and y2 values respectively. So now we can run it through the slope formula and we get 1/2 here. But now here's the question. And by the way, that's it for average rate of change. You're either going to have the graph of a function for which you're going to be able to see what your x and y values are for the points at which you're trying to find the average rate of change for over the specific interval that you're given. Or you're going to have the formula for the function for which you could find the corresponding y values for, since you're going to be given a closed interval. Up till now, we don't know how to find the average rate of change on a non-given interval. Like, you have to know what the interval is in order to find what the average rate of change is. But then that leads directly to this question. Can we find the average rate of change on an interval that's not given? Like, let's just say we're given a function and then somebody says, all right, find the average rate of change of this function. But we don't have an interval, right? So how are we going to do that? It turns out, yeah, we can do this. We can find the average rate of change in an unspecified interval. We're not going to get a number, right? The only way we'd get a number is if we knew what the interval was. So instead, we're going to get like a formula for the average rate of change, which is pretty cool. Here's how we figure that out. Since we're not specifying an interval, what we can do is we can specify a distance between two arbitrary points on the graph. We're going to call the points x, and then we're going to actually define a variable that represents the distance between our second x value, and we're going to call that variable h. And so that is actually the only thing that we define in this entire formula. We're like, let's just let the distance between our two x values be this variable h. And h could be super big, or h could be really small. And x could be literally anywhere, right, on the x-axis, as long as it's in the domain, of the function. Which would make our second x value very simply x plus h, because it's h units away. So good, we have a run, basically, right? You got to think about, we're trying to come up still with a slope. If we're trying to find average rate of change, we need a rise and we need a run. Well, we just now have the change in horizontal distance. We have the quote unquote run here. It's just going to be h. The question is, how are we going to define y based on this choice? Well, we have the function name. So the corresponding y values for x and x plus h are just simply going to be f of x and f of x plus h. So we have these 2 points on the graph. It looks complicated, but it's just x, f of x. That's our first point. X plus h, f of x plus h. Right? That's going to be our second point. And so let's just find the slope. Find the average rate of change. So if you do that, y2 is like your f of x plus h, y1 is f of x, x2 is x plus h, and x1 is just x. So we're subtracting x, which means that this x subtracted this x, right? Those cancel, I guess is what I'm trying to say. And so this is the formula. That is it. That's the difference quotient. So the difference quotient is defined to be the average rate of change on an unspecified interval, on an unspecified closed interval, x to x plus h. And it's given by this formula that we just wrote down. F of x plus h minus f of x over h. So let's see an example of what what did we just do? Like, what is this? So example 3 says, find the difference quotient for k of x, which is x squared minus 2x. It says find the difference quotient, so that means we're finding the average rate of change on the unspecified interval x to x plus h. And the difference quotient is this thing. So we need to do this. We need to find this for k of x. Now to find that, we should probably start by finding this thing, f of x plus h. I guess in our case, though, it's k of x plus h. When you're evaluating a function at an expression, that expression replaces x, or whatever the independent variable is in your function, in our case it is x, with the expression itself. So instead of x, I'm going to write x plus h. So instead of x squared, we have the quantity x plus h squared. Instead of minus 2x, we have minus 2 times the quantity x plus h. And then we got to simplify this thing. So first I'll distribute the negative 2, and then I'll square this binomial x plus h, which, remember, again, is not x squared plus h squared. It's box method, FOIL method, and it gets you to x squared plus 2xh plus h squared, and then we still have the minus 2x minus 2h right here. Okay, that's just this thing. But that's actually the hardest thing to calculate. So at this point, we just need to plug the rest of the stuff in, and I specified the difference quotient here just for k, so k of x plus h minus k of x over h. We know what k of x plus h is. That's this thing here. And then I'm just subtracting k of x. So I stuck k of x right in here. But we're subtracting it, so you're subtracting the whole quantity. And then h is just in the denominator. So now we just simplify. So first I started with distributing the negative sign. That gave me negative x squared and positive 2x because the sign is changing. And then this is how you know you're doing the difference quotient correctly. Everything without an h in it is about to cancel. So these x squareds here, you've got x squared and you've got a negative x squared, so those cancel. Here you've got a negative 2x and a positive 2x. Okay, so those cancel. And then what's left are things that only have an h in it, and because of that, that means that we can actually simplify everything by a factor of h, which means 2xh just becomes 2x, h squared just becomes h, and 2h becomes 2, and our denominator becomes the number 1. So we get this. And you might be thinking to yourself, cool. But like, what did we just do? Right? So let's back up a second and let me explain what it is that we just found. Okay? First of all, we found the difference quotient. So 2x plus h minus 2 is the average rate of change for the k function on the unspecified interval k to k plus h. But who cares, right? This isn't very descriptive. We can't do anything with this. It's just a formula. So let me explain. Let's pretend that this is a different day, time has passed, and someone gives you this problem and says, hey, given k of x, let's say it's x squared minus 2x, find the average rate of change on these 3 intervals, okay? And you're like, oh man, I got to do this 3 different times. I have to do y2 minus y1 over x2 minus x1. Okay, so we got to find the corresponding y values for the x values. So we got to plug in 0, and we got to plug in 2, and we're going to get all this stuff. No, you don't have to do that. We already did that in general. Like, this is y2 minus y1 over x2 minus x1. It is the formula for the average rate of change. So as soon as someone specifies an interval like 0, 2, you can use the difference quotient, because that thing that I just circled is y2 minus y1 over x2 minus x1 in general. It's like a model for the slope of k. You just need to know what is x and what is h. Okay, so in the interval 0 to 2, x is 0, right? X is the first thing in the interval, so here it's 0. H is 2, because it's 0 plus 2 gives us 2, so h must be 2 here. So just plug that into this, right? So 2 times 0, because x is 0, plus 2, because h is 2, minus 2, well, those just cancel, so 0. The average rate of change for k on the closed interval 0 to 2 is 0 by plugging stuff into the difference quotient. In the next one, x is 1, and h is again 2, right? You might be tempted to think that it's 3, but remember, it's the distance between this and this. That's how we defined h. So the distance between 1 and 3 is 2, so we have h is equal to 2 here. So again, we plug the stuff that we know into the difference quotient. X is 1, h is 2, again, these cancel, but 2 times 1 is 2. So the average rate of change for k on the closed interval 1 to 3 is 2. For negative 3, 7, same idea. X is negative 3 there. The distance between negative 3 and 7 is 10. So plugging things into the average rate of change formula to the difference quotient, we get 2. And so that's the really cool thing about the difference quotient. Like you're finding a formula for the average rate of change. And so once you know what an interval is, you can use that formula to then find as many different intervals, rates of changes that you want to find. Now, I'm going to leave you with this thought, okay? Because this is an important question to think about. What if we take the point x plus h and we start moving it closer to x, effectively decreasing h? Like what happens when h gets really, really small to the point where it's basically 0, where x plus h is basically on the point x? Well, that, my friends, is the birth of calculus. This is where calculus comes from, the idea of a limit. You're making h approach 0, and what happens to your average rate of change is that it becomes your instantaneous rate of change. And if you want to learn more, I actually have a video on that. I'll link it in the description below. Okay, so that's it for today. Hopefully you guys learned something. If you have any questions, please leave a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.